and let's start talking about exceptions and interrupts. And then we're going to start talking about superscalars too. So we'll start talking about out-of-order superscalars. So how do you actually start to execute instructions when they're not in programmatic order? And when you first hear about this, you're going to say, well, how is that possible? You shouldn't be able to execute instructions out of order. But it's relatively easy. You can actually just execute them out of order. Maybe you want to commit them in order. That may even be optional. But let's start off by talking about interrupts. So what's an interrupt? So an interrupt is typically some external or internal event that happens, and it may be synchronous to an instruction, or it may just be some external thing that happens that is going to redirect your control flow somewhere else for a little bit of time, and then it'll come back to the instruction that you were at before. So here's our program. It's happily executing instruction I-1. Then it's going to execute instruction I. Instruction I doesn't actually commit. Instead, we vector over here to an interrupt handler, which is also some sequence of instructions that processes some problem, let's say, with instruction I. And then when it's done, it'll come back, re-execute instruction 1, or instruction I. Maybe, maybe not. We'll see why there's some cases that you may not actually go to re-execute this instruction if it has a fatal fault, and then continue on. Typically, I wanted to point out that a lot of times this is done sort of for system-level code or operating system-level code or hypervisor-level code that you'll jump someplace else. So a good example of this is a timer interrupt on a processor. It goes off, and it'll re-vector you to someplace else where you have to sort of update the internal time of the machine, and then you go back to the instruction sequence that you were executing before. So let's look at some of these causes. So we'll name the first set of interrupts here asynchronous interrupts, or some people call these external events or external interrupts. And some good examples, as I said before, are devices cause interrupts. So something like the programmable interrupt timer on x86 processor will cause a timer tick every once in a while, or every 100 times a second is pretty probable. Other devices, your network card gets a packet in on it, and the packet needs to be processed, so it needs to be read off the network and be put into RAM somewhere. Hardware failures, so things like ECC memory errors. So it's error-correcting code memory errors in your main memory will sometimes cause interrupts to happen or asynchronous events to happen. Synchronous things, sometimes people call these exceptions or traps. I'm actually calling all these things interrupts because from a naming perspective, if you read different architectural manuals, they all rename these things slightly different, and there is no sort of common utilization of the terms. But if you're using something like x86, a synchronous interrupt is usually called either a trap or an exception. But that's not common across all other architectures that are not x86. So some good examples of this is if you try to execute an instruction which is not in the ISA manual. It's some gobbledygook of bits on the disk. So it's error code, effectively, or some non-valid instruction. You'll get an illegal instruction exception. Or if you're trying to execute, let's say, an operating system level instruction. We haven't talked about this in great detail. We'll touch on this later in the course. But if you're trying to go execute some instruction that only the operating system should be able to execute, but you're executing it from your user program, then you're trying to execute something like a privilege instruction. That's a good way to have this happen. Arithmetic overflow. Some architectures have it when the precision of your numbers falls outside the scope of what you can actually accurately represent. You'll get an overflow exception or underflow exception. Similar sorts of things can happen in a floating point unit. So a great example of this is if you end up with what are called denormalized numbers. So in floating point numbers, this means you basically have also lost precision in your floating point unit. So you fall out of the range of numbers that they can represent very well, and you end up in this other space that are called denormalized numbers. You'll get an exception, usually. Sometimes other sorts of things that fall in this case are things like divide by 0. If you try to divide by 0, you'll sometimes get exceptions. And you can do that. That's a great way if you on your x86. If you guys want to write a program, write a simple C program, take some number, divide it by 0, and then go and run the program. You'll get a printout. The operating system you'll get an exception. The OS will print out, divide by 0 fault. And your program will stop. It'll kill your program. Unaligned memory. Some architectures don't allow you to access memory in an unaligned manner. Some architectures do. So something like MIPS, the MIPS instruction set, if you go to try to execute a unaligned instruction sequence, or unaligned load, we'll say, on the earlier versions of MIPS, you'll actually get a unaligned memory access. Later MIPS have it as an option. You can either have it take a trap or not take a trap. Common thing, page faults. So we'll be talking about paging later in this course, but if you go to try to access some piece of memory and the memory is not mapped in correctly, so you just can't, the machine physically can't go find memory, you'll take a trap. And then finally, the things like system calls or interrupts on x86, there's an instruction called int, which actually causes just an interrupt to occur, and then it takes as a parameter a number. So that's how system calls have traditionally worked on x86. They later replaced it with actually an instruction called sysenter, which does a similar sort of thing with a little bit cleaner semantics. So I think actually there's one point I wanted to talk about. Asynchronous interrupts is, with asynchronous interrupts, it's hard to know when to deliver the interrupt, because it's not pegged to a specific instruction. And if your instruction is going down the pipeline, you don't necessarily know whether to tag it to the first instruction that's in the pipe. I think it's at the sort of the fetch stage. I think it's at the execute stage. I think it's at the write back stage. So that's a challenge. Another important thing to think about with asynchronous interrupts is sometimes multiple of them go off at the same time. So let's say your timer interrupt goes off at time t equals 0. Your network card gets a packet in, and someone hits the keyboard exactly at the same time. Well, which should happen? Which should you actually go handle? Typically, machines have a prioritized interrupt request mechanism. So there will be some sort of priority encoder there, which will determine which is the highest priority. Some machines will actually have reprogrammable priority interrupt encoders effectively, which will allow the system software, the operating system, to decide what is the highest priority interrupt to go take in that case. Sometimes machines will just sort of make a decision, or the architects of the machine will sort of make a decision and say, these classes of interrupts are not or asynchronous interrupts are not very easy to handle. So we'll just sort of put those in the sort of lower priority bucket, and then some smaller set you'll actually be able to sort of reprioritize, if you will. Oh, yeah. So I wanted to talk about this. What actually happens when you take an interrupt from a hardware mechanism perspective? So this is a very idealized view, but from a mechanical perspective, things need to happen in the machine. There's some state that needs to be updated. First thing that needs to happen is you should basically stop the program at some point, and you should try to save the program counter somewhere. Because if we want to come back to, let's say, the instruction that took the interrupt, we need to know where to come back to. But we're going to go and execute some other piece of code in the meantime. So we can't just save it in the program counter. We need to save it off. And that's typically called either an exceptional PC, so EPC. That's what it's called on a MIPS processor. On x86, I'm trying to remember what it does. I think it actually gets pushed onto a system stack, so it gets put into memory somewhere. And if you look at something like MIPS, one of the tricky things here is all of your registers are still live from the previous instruction sequence here. So all of a sudden, you jump into a new piece of code, and all of your instructions are still, or all of your registers are still live. They have values you can't throw away, and you're in the interrupt exception handler. What do you do? Well, there's different mechanisms to this, to have this happen. Some architectures, something like MIPS, actually reserves 2 registers that are only allowed to be used by interrupt handlers. This is actually a pretty poor solution, in my opinion. So they they save off 2 registers. I believe it's somewhere high. It's I think maybe 28 and 29. Register 28 and 29 are not allowed to be used by the basically operating system or the user code, and it's only used by the interrupt handlers in the operating system to save off state. And what happens in that case is you could use those registers to basically take the other registers, compute some addresses, and do a store, because if you recall on MIPS, you need to have an address to do the store to. So you compose the address into, let's say, register 28, and then use that as the store address, and you can store off all of the other registers into memory somewhere. And then you can unwind that back when you're going to return from the interrupt. So it's a complicated dance. Something like x86, there's some hardware mechanisms there which will actually take it and take a lot of your registers and put them onto a in-memory stack for you. So it's typically what's either a push A, which is a push all, pushes all the register state onto the stack, and a pop A, which pops it off. That's not actually required, though. There's other, some operating systems don't actually do push A and pop A. Better operating systems or more modern operating systems will actually only save off what is strictly needed. That's something to think about. One other important thing here, typically when an interrupt occurs, you probably want to mask other interrupts from happening. So this is a really hard problem to solve, is you have interrupts inside of an interrupt handler. Ooh, that doesn't sound like a happy day for anyone. Because what if you're in an interrupt handler, another external interrupt comes in, what do you do? You can't save the exceptional PC into the exceptional PC state now, because you've already saved the old program counter into there. You can't take that second interrupt inside of that, so you can't necessarily nest interrupts very easily. So what people do for this is, one solution actually is to take the exceptional PC and put it into memory somewhere. And once you've done that, then you can turn interrupts back on inside the interrupt handler. You can take more interrupts inside the interrupt handler. Alternatively, if you know that the interrupt's going to resolve itself very quickly, you can just leave interrupts masked the whole time the interrupt handler is happening. And when it's done, just the return from interrupt instruction usually turns off the interrupt. Or excuse me, turns back on the interrupts, if you will. So it'll re-enable interrupts. So you gotta be a little careful there. There's with interrupts inside of interrupts happening. So that's a great question. So what do you save in the exceptional PC on a interrupt? Oops. So yeah, that's a great question. So if you have instructions sort of marching down the pipe in a two-way in-order superscalar, we'll say, you're going to save the PC of the instruction that took the interrupt. Some architectures define this differently. If you go look at something like x86, typically what gets saved in the exceptional PC is the next instruction to execute. So it's really dependent on architectures. Some architectures will save the address in the exceptional PC of the next instruction in program order to execute. Some things will save the address of the instruction that actually took the trap. And as far as, or took the exception or the interrupt, so it's a little bit of a trade-off there. One thing that's actually hard is if you have a branch that takes an exception, do you store the target of the branch location in the exceptional PC, or do you, you have to sort of resolve the branch first. So that's one reason actually why lots of architectures favor just storing the PC of the instruction that took the trap and not the sort of quote unquote next instruction. So I actually favor storing the PC of the instruction that took the trap and not the destination of that. Synchronous interrupts, similar sort of thing. Sometimes the handler wants to resume after sort of an instruction, so it might have to add PC plus 4 if you have an architecture, exceptional PC plus 4 if you need to jump over the instruction, for instance. Something I did want, so here, this is the next question that came up was, what does this look like in a pipeline? And when do you know to actually process the interrupt? So here we have a 5-stage pipe. So it's a little bit easier pipeline. And we can see these bubbles here are actually different types of interrupts or exceptions that can come out of the pipe at different locations. So out in front here, we can have maybe PC address exception. What do I mean by that? Well, some architectures won't allow you to execute, let's say, code out of certain regions of memory. So an example of this actually is in the 64-bit extension of x86. The 64-bit extension of x86, there's what they call the memory hole. So between what people call positive memory and negative memory, so the top bit being set, there's a big chunk of memory which is just no one's allowed to execute out of, or it's not mapped, it's not real memory. So they have a 64-bit address space, but they only use 42 bits of that 64-bit address space. So if you have any bits in the middle which are not set correctly, you're basically going to be executing out of the memory hole. And that's an example of something which can cause a PC address exception. So your PC sort of falls off the end of mapped memory. What do? You're in some piece of memory, you're in some address which by definition is not a valid address. Decode, illegal opcode. So it isn't in your ISA manual. There's lots of opcode and coding space. Usually, most architectures purposely leave some space in there just for legal instructions or future expansion, if you will. And you want that to interrupt overflows and underflows out of your ALU. There's a whole host, if you have a floating point unit here, of floating point exceptions, overflows, underflows, and denormalized sorts of instructions. Data address exceptions. Well, this could be if let's say you have an unmapped memory address, or you do a unaligned load or store. So basically every stage of your pipe here can be generating some form of interrupt. And then there's also asynchronous interrupts, which we haven't drawn yet. OK, so good first question here is how do we handle multiple simultaneous interrupts in different pipeline stages happening all at the same time? I agree we should prioritize them. So what is the oldest instruction in the pipeline here? So this is going to be the oldest instruction in the pipe. So let's think about that. So that means it's probably going to want to kill everything behind it if there is an exception that has happened here. So if we were sort of have multiple things generating exceptions here at the same time, the oldest thing, the oldest instruction in the pipe, the instruction that's been in the pipe the longest, is going to want to kill all the rest of the things. Going forward, though, so from a priority perspective, which of these things are probably the highest priority? So do you think we should be computing overflow errors if the instruction opcode is illegal? Should we be even decoding the instruction if the address that we try to fetch from our instruction memory doesn't make any sense? So the priority of sort of when you go to figure out where or which exception or which interrupt is the cause of the exception should go this way from left to right. And then you're going to want to actually kill going backwards. So let's skip that question for a second and look at this drawing. So what you'll see here is we're actually going to just remember that we took some exception for a particular instruction and just pipe it forward. And then what we're going to do is we're basically going to say at the end of the pipe, once we know everything that's happened, we're going to call this the commit point. And that's going to feed back the other way, killing everything. Now, why do we put the commit point here? Could we put the commit point, let's say, in this stage of the pipe, in the execute stage? So let's define the commit point. The commit point is the point at which architectural state of the machine is committed to is committed, and Now, that may not be in the register file yet, because by definition, in this point here, it's not in the register file. It doesn't get there to the write back stage. But nothing can change. We can't take a branch. We can't redirect. We can't take any more exceptions. Well, by that definition, we can't put the commit point here because further exceptions can happen after the commit point if we pull the commit point back. There are machines which do pull the commit point back. You will see when we start talking about superscale or out-of-order superscalars, we typically like to have the commit point at the end, or near the end, because then you can sort of see if everything's resolved. You can handle your interrupts and exceptions and have exceptions going on in the pipe as long as possible. And if you try to pull your commit point early, that forces you to actually resolve if whether an exception is going to happen for a particular instruction relatively early in the pipe. So if we want to pull this forward a stage, we would have to basically check whether the address of a load or store is valid in this pipe stage. That may be possible because we finished the calculation of the address right here, but we haven't necessarily, let's say, done the TLB lookup. But we can pull the TLB lookup earlier or something like that. That is possible. And we'll see that some architectures try to pull that early. Some architectures also try to have imprecise exceptions. This is a scary, scary place. We're not going to be talking about this very much. We're going to be talking about precise exceptions mostly in this class. But an imprecise exception is one where instructions are going on the pipe. You basically let the instruction sort of pass the commit point, and you tag the exception to the wrong instruction effectively. It's not precise. You can't stop on a dime. Architectures, there are some embedded processors that do things like that. And it's probably not the wisest thing to do if you want to run a real operating system. But like I said, yeah, so the commit point being close to the end is probably a good place, or at least after all your exceptions are done. So by the time we get to this red dashed line here, so we're after the computation of the exceptional PC and everything, we know that we're going to be committing. Or at least we have a thumbs up or a thumbs down. And if it's a thumbs down, we kill everything behind here. One thing I did want to say is cause. What does that register do? Well, that register tells us why did we take the exception. So it's a priority encoder, which prioritizes, as we said, this direction, and will determine the cause of the exception. Asynchronous interrupts. There's different places to wire this in. You just sort of have to tag it to something, but you have to make sure you actually take it. So the simplest thing to do is just to put it into this big logic at the end of the pipe here at the commit point, and have the asynchronous interrupt show up at the end of the pipe. Not all pipes do this. Some pipes will actually inject an asynchronous interrupt at the beginning of the pipe, allow it to go down the end, and arbitrate like everything else here at the end stage of the pipe. The simplest thing to do is to have it come in here, and that's because otherwise you might drop this asynchronous interrupt on the ground or not actually take the asynchronous interrupt, and you want to make sure you actually have a chance to take it. Exceptional PC takes the PC and pipes it forward and saves that in a register, but this only gets loaded on a exception or interrupt happening. Okay, so that's commit points. That's important for out-of-order superscalars because we're going to have to start thinking about where is the commit point of a processor, and it may not be where we want it. Or it's possible that we will not be able to put the commit point anywhere in the processor and actually have the processor work. So today we're going to actually look at a processor where it's not possible to have precise exceptions. So there is no line we can cut and say this is the commit point. Let's see. So we covered all this. Speculation. This is going back to like our example of PC plus 4. Do we want to assume the exception is going to happen, or the interrupt is going to happen, or not? So we're calling it an exception for a reason. It is the exceptional case. It is not the common case. So we want to somehow predict what our branch predictor tells us, or PC plus 4, or fall through, or PC, the next instruction. We do not want to just have, we don't have to wait to the end of the pipe to know whether an exception is taken or not before we try to go get the next instruction. One other thing. When we start to go to out-of-order pipelines, we're going to start to need some recovery mechanism here. We're going to be processing instructions out of order. So if we might be taking an interrupt for an instruction after its let's say, subsequent instructions have either committed or sort of started to go down the pipe, and you start to get some out-of-order time questions. So we're going to look at a few different solutions to this for recovery. In our simple cases, we just basically flush the pipe and kill everything behind us. In more complicated things, we're actually going to have extra register files that are basically going to be shadow register files. They're going to keep track of everything that's going on in the processor, of what should have happened, and then we're going to dump that into our true into our physical register file, and we'll look at that maybe today or next class. We should bypass. Bypassing is good. You should not have to wait to the end of the pipe. Okay, so let's look at a time diagram here of an add that takes an overflow. Instruction 1 here is an add, and we speculate that it does not take any sort of exception. So we fetch the next instruction. We start sticking that down the pipe. In the execute stage of the pipe, we determine that there is an overflow. But as we said, we don't actually try to do anything about this until the commit stage of the pipe. So in our simple pipe, our commit stage is at the end of this memory stage. So we actually pipe it forward one stage. At that point, we restart the front of the pipe, and we start fetching the handler code, the exceptional handler code. And we're going to basically kill behind us, turn everything behind us into a no-op. So let's say we're bypassing out of EX1 here into the, well, OK, let's say we go to this one instead. Or we can come out of here. Let's say we're bypassing out of the memory stage, or the memory stage, back to the register fetch stage of instruction 3. I think that's what you just asked about. What's going to happen is we're going to let that bypass happen. We're going to let that data come around through the bypass network. But what's going to happen is at that same time, we're sending the kill signal behind us in the pipe. Or instruction 1 is going to be killing everything behind it in the pipe. So we're going to bypass the data around. It's going to get bypassed. It's going to end up in the pipeline register at the end of that cycle. But it's going to be killed basically in the end of that cycle. A better example is actually here. Let's say it bypasses to instruction 2 from the execute stage to the decode stage of the pipe. That's actually going to get loaded into the pipeline register of the fetched operand. And that's going to go forward into the execute stage, EX2 here, for instruction 2. So we bypassed it. We started executing that instruction. Everything was going fine. But then we just come along and we kill it. So we're speculatively executing, it's called. So it's a speculative execution pipeline. We are assuming and we're predicting that everything is going fine. And then we're going to be killing behind us when something goes wrong.